is kind of desired. That's the term in this principle, but that is a big research question. So better noise distribution leads to better landscape of the objective. And recently, one of the author of this original paper with his collaborator published conditional version of NC to address this problem. So that is one possibility. So I'm gonna touch on that if time permits briefly at the end of the talk, but yeah. So I just want to highlight that this is a big problem. Right, and okay, yep, question?
Yeah, so yeah, I totally understand that if the noise distribution is similar to the data generative distribution, classification gets harder. So the parameter needs to be estimated better. But if actually the noise distribution is the data distribution, wouldn't the classification problem be impossible? So if the two are the same, I guess the optimal base error would be half because because they have the same distribution.
Right, yeah. So yeah, to my understanding, there should be no, okay. Right, so technically there should be no problem, but you cannot use the data generating distribution in place of the noise distribution because you don't know how to evaluate the density with respect to the data generating distribution. It is as hard as modeling the data generating distribution.
So technically, that's almost impossible to happen.
So if you want to use the data generating distribution in place of this, so first of all, you can sample from samples. I mean, basically you are given samples from the data generating distribution, so we can do that. But the problem is that you cannot evaluate the density PDX tilde without any model. So if you want to do so, you should learn another model that can approximate the data generating distribution, but that is kind of deviated too much.
Oh, I see.
But technically, you can use the data generating distribution. That's my understanding. Yeah.
Okay.
Yep. Right. Yep.
I have a question just about this optimization. It looks like as if you can get a very good, you can make the objective function very high just by having a phi, your predicted distribution to be something that is very different from the noise distribution, but not necessarily a good match for the data distribution. I understand that the theorem, like the global minima is going to be the global minima of phi is going to be close to the data distribution, but in practice, will this converge to some sort of like local minima way like before that, or?
Yeah, that could happen. But I mean, depending on the model and the underlying distribution and so on. Yeah. Yeah. So the only thing we can ensure is that at the global minima, we can recover the parameter.
Okay, yeah.
Yeah, but the fine landscape of the objective function is kind of difficult to analyze, or yeah. I mean, it could be possible for simple models, but yeah. Right.
So you need to like tune the learning rate a lot, I guess, when you're doing this.
Yeah, I can't tell.
So I can see a situation where you have this thing where it's like my guess for what the distribution is just very different from the noise, but it's not necessarily close to data distribution, and you would still get a very nice objective function.
Yeah, so but if your model distribution is nice, I mean, rich enough, and yeah, I don't know. Yeah, I'll not tell much about what I don't know. And there's a question in the chat, another comment and question on slide 10. I find it interesting to compare KL divergence with this J. Yeah, actually, I'm gonna, yeah, in the second part, I'm gonna give you that this yeah, at the if it is maximized, this can be viewed as Jensen-Shahn divergence. That's what I'm gonna talk about in the second part. So yeah, thanks for the comment. So it's related to Jensen-Shahn divergence. Yeah. Right. So if there is no further question, let me give you the generalization part. So let's recap the NC principle. So this is the NC objective, and this is what we use in practice with samples. And this can be generalized with F divergences. That's what I'm gonna talk about. So here's the digression with F divergences. So this notion was introduced by several persons. Like one is Chijar from information theory. So given a convex function f with f1 being 0, so this is actually not a strong constraint, because you can actually subtract and add any random numbers, real numbers to it. So the F divergence is defined as the integral of Qx times F of the density ratio between P and Q. Okay, so this this plays a central role in information theory and machine learning, and it subsumes a lot of interesting divergences. For example, KL divergence. If you let FR to be R log R, then it recovers the KL divergence, the PQ. And if you use FR to be R to the alpha, so technically speaking, you should take the subtraction here with 1. But this gives you the alpha divergence, which is based, the Renyi divergence is a function of alpha divergence and so on. And the Jensen-Shahn divergence, which is defined as the KL divergence of P with respect to P plus Q over 2. And this is also falls into this class with a specific choice of F function, right? So I'm gonna introduce a variational characterization of F divergences, and I'm gonna borrow a very mild, very light technical tools from convex analysis. So given a convex function F, we define the Fenchel dual function of it by the following. So we are going to use F star U, and I'm going to just assume this real line, no high dimensional space. So on the real line, the Fenchel dual is defined as the supremum of R times U minus FR over R, the real number. And there are two facts. So it is, this one is really easy to show. So FR plus F star U is always greater than equal to R times U. And this can be viewed as, since if you remove this supremum and replace this by inequality, then yeah, this is equivalent to this. And this has a fancy name, Fenchel-Young inequality. And fact 2 is that if function f is nice enough in the sense that it's convex, proper, lower semi-continuous, and differentiable, then the equality condition of this Fenchel-Young inequality is if equivalent to U to be F prime R. Right, so let's believe that this is true. So these are well-known facts. And I'm gonna analyze the F divergence. So what I'm gonna do is I'm gonna apply the Fenchel-Young inequality to this term. And then this F of P over Q is lower bounded by U times P over Q minus F star of U. And rearranging the term will give you the integral of ux px dx minus integral of f star ux qx dx. And by the equality condition here, the equality holds if and only if ux is f prime of p over q for any x. Okay. So this is what we just proved. So if f is convex, I mean, if f is nice enough, then the f divergence can be characterized as the maximization of this if function, which is a function of r, p, and q, where if r, p, q is defined as the expected value of this one under px, and expected value of this one at qx. And the maximum is attained if and only if Rx happens to be consistent with the density ratio between P and Q for every x. Right. And now I'm gonna instantiate in the context of noise contrastive estimation. So I'm gonna plug in PD and the data distribution, and the noise distribution for Q. Then what we get is if F is nice enough, then the maximization, F divergence is can be written in this form, and the zeta star is actually the argmax of this, where the JF zeta is defined by this function. And R theta is parameterized by phi tilde over Pn. Right, then based on this, I'm defining the F noise contrastive estimation principle. So instead of the previous, the expected value of log of something plus log of, expected value of log something, we can replace that with this form. And with samples, we can also instantiate this with the summations. Right, then you might ask why this is a proper generalization of the original NCE. So let me give you, let me justify why that's the case. So I mentioned that if you choose FR to be this, then this will give you the Jensen-Shine divergence. And we saw that it can be expressed as the maximization of some function. And that is, it's just this, right? And let's compute this one. So for this FR, if you compute the derivative, you can easily show that this is log of 2R over 1 plus R. And you can also compute the Fenchel-Dior very easily by differentiation. And if you plug in this into this, then you get this. And if you plug in these terms to this expression, what you get is expected value of log R over 1 plus R under P, and expected value of log 1 over 1 plus R under Q, plus some constant. And if you recall the NC objective, which was the expected value of log of phi tilde over phi tilde plus Pn under PD, and so on. If you take R theta to be phi tilde theta over Pn, then you can see that the NC objective is equivalent to this IJS up to constant, up to additional constant. So it's equivalent. So when you instantiate the FNC with Jensen-Schwann divergence, then that will recover the original NC. Right? Now then we can just plug in whatever F divergence you want. So one possibility is, for example, we can take the chi-square divergence, which is defined with the choice of FR to be R squared minus 1. Then the chi-square divergence is defined as, given as this.